Before we move into the 3-electron group case, I just want to highlight something that came up in passing with the 2-electron groups. But I want to bring it up now because I want to make this strong distinction between why we have to make something more complicated. So you can see here, if I sketch something up here, let's just say that we have the beryllium example. And let's make it even simpler versus the last time. We'll just make both of these hydrogens. You can see that we have electrons here and electrons here. Now suppose that I got rid of that hydrogen. That would make this into an electron pair. I'm going to go ahead and grab an eraser. And I'll grab my pen again. And we'll make it into an electron pair. Now we could go ahead and try writing it as a different AXE geometry. So instead of it being AX2, now this would be AXE. But here's the thing I want to emphasize. What's the point? Why bother writing that? If we don't have an atom on both of these ends, so that we actually do have an electron group somewhere, well then, all we're really doing is saying that this is an end. It's not a central atom anymore. And that's really what we're using this geometry terminology for. So we just generally won't bring that one up. But if we actually are going to have the ability to still be a central atom by having another direction where there's a bond, say we had something like this with a triangle, like trigonal pyramidal. Now we can actually have the case where, even with an electron pair in there, we can still have a geometry that's meaningful other than just saying it's a dead end. Now we're going to have to make a distinction between our electron group geometry and our molecular geometries. So you can see at the very top we had trigonal planar for our electron group geometry. Down here we're going to look at the molecular shape. Now this is when we're only going to care about the atoms. Now some of you may have been always counting them by thinking of how many atoms were at the ends. Don't do that. Only do that for molecular shape. Remember, electron group arrangement. Focus on where the electrons are when you're doing your electron group arrangements. Because we're going to find out some weird distinctions here in a second. Now if we have an atom on the end of each of those, and we get rid of that gray triangle in the background, we'd say, yep, that's a trigonal planar electron group arrangement, and it's a trigonal planar molecular shape. Electron group shape, electron group arrangement, we'll use those phrases totally interchangeably, so don't let that throw you at all. But what if one of those was actually an electron pair instead of an atom at the end of it? Notice, if we're doing our electron group geometry, one group, two groups, three groups, it's still going to be trigonal planar for the electron group arrangement. But when we talk about the molecular shape, though, where we're only concerned with where the atoms are, you can see that this is now a bent shape. And that's actually going to be the word we're going to use for that. It's going to be a bent or a V-shaped geometry. And its notation would be AX2E. And let me just show why the E again. AX2E. Now the 120 degrees is something that's important to remember about that. And I want you to have that memorized alongside of our 3-electron group family of geometries. Because we're going to see another case in a minute with a bent geometry. And we're going to have a different angle. So that angle is going to be what lets us distinguish between our geometries if all we know is the shape of the molecule. Now, we could replace another atom with an electron pair. But again, this is the same thing I was bringing up a moment ago with why we didn't specify molecular shapes for the previous 2-electron group case. Because now we've only got two atoms, and it's going to be a linear shape, and it's going to be a dead end on the molecule. So linear AXE2. We generally aren't going to talk about that shape at all. But just for completion, I have it shown here.